In this section, we're going to talk about measures of dispersion. And the word dispersion means like how spread out something is. So what we're really getting to here is we're going to talk about statistics, and we're going to talk about how spread out is our data. That's pretty much it. Now, we're going to use one vocabulary word called variance. We're going to use that to describe how spread out our data is. We're going to find the relationship, and now notice it says calculate variance. Okay, but then calculate and describe standard deviation. We're going to use variance to get to standard deviation and understand the meaning of standard deviation. It's going to be far more important in this class. Not saying variance isn't important in general, just not in this class as much. Then we're going to also find the rule of 68, 95, 99.7. And then last but not least, we're going to talk about Chevyshev's rule. Okay, let's get started. Now, because we're talking about data, the very first thing we have to say is, do we know the difference between a sample and a population? Now, I'm going to leave the heavy lifting of this concept to your statistics courses, but just in general, just so you have a basic idea, a sample is a subset of the population. Okay, so when we're doing statistics, when we're calculating statistics, what we're trying to do is grab a small group of people that represent the entire population, that represent the entire people. So, for example, during elections, when we try to survey a few thousand people about who they want to be president or senator or whatever, and then use that to make a prediction about the entire population. And there's a lot of methodology to this to make it valid, more or less valid, and you'll quite enjoy that. Once you understand the methodology, you'll enjoy what happens when you actually watch elections and the things that occur on TV. Nonetheless, so sample is a small group, population is the entire group you're trying to describe. Okay, so what we're going to start off with is the equation for variance of a sample. So the equation here is fantastic. There's a lot going on here. So I'm going to break it down piece by piece. Whenever you see an x sub k, that is just one data point. Now, when I say x sub k, that would be like this one right here, x sub 1, x sub 2, x sub n. What we mean is just one bit of data. So this would be the first person I interviewed, the second person I interviewed, and so on and so forth until I get to my nth person, which would be the last person I interviewed. Okay, so that's all we mean by the x sub k. X sub r is average. Now remember, I'm going to use the word average in quotations, because that does not mean mean. It can mean mean. Mean is acceptable, right? That is a version of average. But what we're saying is any appropriate version of average. So it could be mean, it could be median, it could be expected value, right? It could be any kind of average. All right, N is the number of people, or number of, let's call it data points. Data points. So it could be a number of people interviewed, number of shoe sizes measured, whatever you were surveying. Okay, so then and then S squared is your, whoops, let me change colors. That is your variance. Okay, so don't let the squared get to you. Just that's how we notate variance of a sample. Okay, when we go to population, it's going to be very similar. Just we're going to change our letters, but pretty similar. So what's happening here? What is this saying? Take your data point, right? That's what this piece is. Subtract your mean, subtract your average. Then take those values and square them. Then rinse and repeat. Do that for your second data point, third data point, fourth data point, fifth data point. Do that for all of them. And then add all of them together. So there is a common way of writing this using sigma notation. I'm just not going to do that in this class, but you can write it something like this if you are familiar with sigma notation. And then this entire thing divided by n minus 1. This would mean the same thing, but this notation, it's not worth our time in this class. We spend so little time on this that we'll just write it out this way, and we're fine. So I hope this makes sense. I hope this formula makes sense. So now all we're going to do is do it, and then we'll talk about what it means as best we can. All right, so Using the shoe sizes that were from the previous lesson, let's calculate the variance of shoe sizes. So that formula, all right, so the first thing we're going to need to do to get our shoe sizes, we need to know our mean. And just to make life simple, we are going to just use X bar. We'll use the mean, even though I said that's not in the last lesson, I said that's not the best descriptor of mean. And this would be an interesting one because it's bimodal. So we'd have to actually two variances, one for the boys, one for the girls. All right. But just for this example, we'll just use the mean we found in the previous problem. And I had to look back, and that mean was 7.23. So let's go back now, and let's go to our lesson. All right, so our mean is going to be 7.23. Now, our values are all listed up here, right? We've got all those already set out. And then what other information do we need? We need our n, and our n was our number of data points. How many data points do we have? 13. Okay. So I believe we now have everything we need, so let's start writing out our equation. So s squared is equal to, all right, my first data point. So 1 minus 7.23 quantity squared, plus my next data point, 4 minus 7.23 quantity squared, plus my next data point, 4 minus 7.23. Well, aren't we just going to have that same thing twice? So instead of writing it out, why don't we just do 2 of those? So 2 times 4 minus. Okay. Plus our next data point, which would be 5 minus 7.23 squared. Plus, all right, now our next data point would be the value 6. 6 minus 7.23 quantity squared. And we had 3 of those, so I'm going to say 3 of those. All right. Plus, our next data point is 7. So it would be 7 minus 7.23 quantity squared. Then we have 10. Oh, goodness. Okay, so here we go. 10 minus 7.23 quantity squared. Oh my goodness. Now we got 11. All right, yes, I am doing this on purpose, kind of making it long, because it's going to make you appreciate the fast version that comes later. All right, and then 12. 12 minus 7.23 quantity squared. Okay. Oh my goodness. All right, so we got that. Oh, wow. All of that is divided by 13 minus 1. Right? Okay, so now let's calculate. Let's calculate. Holy goodness. Pause the video, do all this by hand, and we're going to cry a little bit, but let's get it done. Okay, I just did it in my calculator, and I got s squared is equal to 11.85897-ish. Okay, now I'm going to tell you the truth. I cheated. I used my calculator, and that's what I'm going to show you how to do now. But this is how you would do this if you didn't use a calculator. So what we're going to do, we're going to open up our calculator. Okay, and in our calculator, we are now going to go to the stat button because we're verging into the world of statistics. We're going to go into here. And then we are going to edit. Choice number 1, we hit enter. Now in here, we're going to put our lists. Now, the way I want you to put in the list is just put in each unique number. So I'm going to put in 1, then hit enter. Then 4, hit enter. 5, 6, 7, 10, 11, and 12. Okay. So each unique number. Then in your L2 list, so you arrow over to the right, so you're in L2, what you're going to do is enter how many of each there were. So I had one number 1, I had 2 number 4s, 1 5, 3 6s, 1 7, 1 10, 3 11s, and 1 12. All right. Now, for those of you who had something in your list and you need to get it cleared out, or when you're doing another problem and you need to get it cleared out, if you have values in your list, you need them to go away. Here's how you do it. You arrow up to the very, very top. Whatever you do, do not press delete, because then your the whole L2, L1, L3 will go away and you will lose it. Instead, what you're going to do is press clear right below the down arrow in the directional pad. You're going to clear, then hit enter, and that will clear out the data. Okay? All right, so now we have our values in for L1 and L2. Now what we're going to do is we're going to quit out to the main screen, Make sure there's nothing on there. So I hit clear. And now we're going to go back to stat. We're going to go to stat. We're going to arrow to calc because we want to calculate something. And in this class, we're only going to do one variable statistics. So a single variable, one shoe size. We're not going to pair it up with two variables such as shoe size correlated to age or something like that. So just one variable. So we hit enter. Now, where did we put our list of values? That was in L1. Then where did we put our frequency list, meaning the list of how frequently these things occurred? Well, that was in our L2. So notice for the frequency list, I'm going to press second 2 because that's the L2 button right there. Now when I go to arrow down, I hit calculate. It's going to give me all of that. Now, for those of you with the old operating system, you may be saying, I typed in all my stuff and I got this. So how do I get my list and my frequency list? Well, for you, it's actually quite simple. It's the same button pushing. You just don't get the visual layout. So here it is. We have one variable statistics, and the first thing we're going to do is put in our list. So we're going to press second 1, and that says this is saying I want to use my L1 as my list of values. Then we're going to put a comma, and then we're going to do second 2 to do L2. So that is your frequency list. So just note the first thing you put in is the list of variables. Then the second is the frequency that they occurred. So then when we hit enter, you should get the exact same thing we got in the other screen. But how I got this 11.85897 came from this screen right here. So if you're not seeing it, that's okay. Hang on. We'll get back to it. But what you will notice right here at the top, X bar, aka our mean, is 7.2307. Yay! Okay, so this stuff is starting to pop out. All right, so we'll come back to this. So if you didn't get that number, don't worry about it. We're going to get it from a calculator. Just hold your horses. All right. Standard deviation. Oh, sorry, I got to talk about what this means. Before we go to standard deviation. Variance. All right, so what we're talking about here is how spread out your data is. Now, variance kind of looks at it from this perspective. This is my average. 7.23 is my average. And I have a data point of 1. So if you kind of imagine plotting your data points on some kind of graph, it might look, not our particular data here, but if you were to plot your data, it might look something like this. And I'm sure at some point in one of your classes, you've learned to draw lines of best fit, and you use your calculator for it, regression equations, all that kind of stuff. Well, what's happening is we're looking at the line of best fit as the quote-unquote average. And what we're saying is how far away are each of my data points from the average. So if we take the data point and subtract the actual value, we'd be getting a distance between our point and our line. Now, if that distance is really far off, that's bad. And so what this equation does is by squaring it, we're kind of punishing you, right? Because 1 minus 7, that's like 6. 6 squared is 36. That's a pretty big punishment, right? And if you think of it as the bigger the number is, the more spread out your data is. This is saying this is really spread out. This is really off, right? And then so on and so forth. 4 minus 7, well, so 4 minus 7-ish, that would be 3. So 3 squared is 9, not nearly 36. And since I have 2 of those, that helps me out, right? Those have less error. And then if you have a value that's very close to your average, such as this one right here, 7 minus 7.23, now that's only 0.23 squared. And when we multiply decimals, a value that's less than 1, they actually get smaller. So therefore that helps us. That's like a little reward. So the idea here is we're taking our error, and if it's really far off, we're punishing ourselves. And if it's really close, we're saying, yay, go us. Then we say, take that amount of error and divide it by not our number of values, which is 13, but we only get to divide it by 12. So that's punishing us even more. So it's making the number a little bit bigger, because if we divide it by 13, it's going to say we have less error, but we're not. We're saying we're dividing by 12, so it breaks it up into less groups. Punishment. Now, if you had 100 minus 1, it doesn't hurt as much, right? So what this is doing is it's kind of punishing you for bad samples. If you only had a sample of 4 people, well, your variance is going to look bigger. Because you didn't sample enough people. Bad you for only sampling 4 people. So that's kind of the idea of what's going on here. All right, that's about all you need to know. So going on to standard deviation. Standard deviation. Same data set, right? Now, before we go on to that though, look at this formula. What's different? Yeah, if you've noticed, the squared from the variance equation has gone away. So essentially, like they took the square root of the left, took the square root of the right, and now we have standard deviation. Yay! Okay, so the calculator doesn't give you variance, it gives you standard deviation. It's something that gets used a lot more, at least in my world that I live in, the regular human being world. Statisticians may use variance a lot, and it may be used a lot in specific um, um, specific industries. There's the word I'm looking for. But if you go to the doctor, they a lot of times will mention standard deviation. When you read studies, they use standard deviation. It's just something that's used a lot. But the idea here, so now what we're doing is looking for an S. Now notice right here it says S sub x. Okay, I'm going to drop this into here. So the S sub x, so I can make it bigger, is just their way of saying it's the standard deviation of the variable. All right, so now how does standard deviation, so if S equals 3.443686159, if that's standard deviation, how do I get it to variance? Well, variance is S squared, so therefore I just take this value and square it. So that's how I cheated and got that number. Yeah, please don't do all that work by hand. Just do it this way. Okay, so standard deviation. We already have it, right? How do we do it? Well, it's right here. So the standard deviation is 3.4436 and change. All right, fine. And the units on it are shoe sizes. It has the same units as our regular units. So if these are representing shoe sizes, the standard deviation is in shoe sizes. Now, here's the important part. What does it mean? How do we read it? Great. You can calculate it. You can type in your calculator. You can get a number. Fantastic. How does that help you? Well, the idea here is if I had some kind of curve where my data was distributed, and in this particular one, we said our mean was what? 7.2. 7.2. Well, before we even do that, let's just do it generically. X bar. What we're describing was, when we talk about standard deviations, is how far off of normal are you? When we say normal, what we mean is average. Okay, how far off of average? How far off of normal? Well, and then we're going to go one standard deviation up and one standard deviation down. So if our mean was 7.2, go away. 7.2, and I add one standard deviation up, which is, let's just call it 3.4. What does 7.2 plus 3.4 make? Well, that makes 10.6. So 10.6 is up, and then minus 3.4 would be one standard deviation down. So 7.2 minus 3.4, that comes out to be 3.8, right? Double check me. Yeah, we're good. So what we're saying is, if we were to describe the group of people who were one standard deviation within the mean, what we're saying is everybody who is in this area, so 3.4 shoe sizes up from the normal and 3.4 shoe sizes down from the normal. And since we weren't dealing with decimal shoe sizes, maybe we would call these people a 10.5, and then these people on the bottom end a 4. So what we're saying is people who have a shoe size between 4 and 10.5 are quote unquote normal. They're average. Your shoe sizes will be carried in a store. If you need to go buy your shoes, they will be on the shelf, right? Kind of normal. Then what would two standard deviations of the mean be? Well, that means we just go up another 3.4 and we go down another 3.4. So people who are two standard deviations in the mean will have a shoe size of what? 14, and the low end would be a 0.4. So now, people who are within two standard deviations, are these people normal? Well, they're not abnormal. It's not that far out of the realm to say a size 14. I mean, when you go into Foot Locker, they're not going to have a gigantic catalog of size 14 shoes. but they may have one or two. And same thing here. I don't even know if there is such thing as a size 0, but you might be getting into kid sizes or something. I don't know. But the idea is you're starting to push the boundaries of average, but you're not talking about anything out of the really ordinary into the extraordinary. It still happens in everyday life. People you know. Now, let's talk about 3 standard deviations of the mean. What on earth does 3 standard deviations of the mean be? Well, with the shoe sizes, this is getting a little interesting now because now we're in negative shoe sizes. So we are definitely in the kid sizes at this point. So if we were talking about adults, I don't know what a -3 would be, but we're talking really small feet, right? That's kind of, for a full-grown adult to have that small of a foot, like a size 10 in kids or something, that would be very abnormal. Okay? Not that there's anything wrong with it, it would just be abnormal. All right, so then same thing the other way. For a size 17.4 shoe, how many people out there, raise your hand if you wear a size 17? Yep, not many of you just raised your hands. Now, to give you an idea of what this means, we when we're talking about quote unquote normal, I believe there's a gentleman by the name of Yao Ming who is 7'5". That is not quote unquote normal. There's nothing wrong with him being that tall, right? But you notice him. It stands out, right? I believe, if I remember correctly, he is 5 standard deviations of the mean. So we'd have to keep going with this to get to 5 standard deviations. But what is 3 standard deviations? If I remember correctly, I believe that would be 6'9" in height. So if you were walking through the mall and you see somebody who is 6'9", you notice them, right? They're tall. So that's kind of the idea, is what we're getting at here. How we look at standard deviation is a measurement of how far off of the mean is your data. So if it's 3 standard deviations away, it's abnormal. For us local Phoenix people, 3 standard deviations of the mean is Larry Fitzgerald, if you're a Cardinals fan, right? The rest of the Cardinals mostly are in the yellow, a few in the 2 standard deviations, but we've got one abnormal player in our team. We have one superstar. Maybe David Johnson sneak into that category, but you got one superstar and it's Larry. Okay? That's the idea. All right. Now, we know how to calculate standard deviation. We know what it means. It's just a descriptor of how far off normal are you. Great. Okay. Now, how do we do this for population? So let's start with variance again. Notice squared. Okay. So this symbol here means variance, just like the previous one. Instead of being an S, now we have a sigma. All right, whatever. Now, this letter here is mu. I don't really care if you know how to say it. All it means is the average. But instead of being the average of a sample, it's the average of an entire population. What's changed? Oh yeah, that's right, nothing. Okay, this formula is the same as the other one, except for, notice down here, there's no penalty. Because if we have literally asked everybody in our population, we have sampled the entire population and asked them who they're going to vote for president, there is no reason we should get penalized for the dividing by the number of people we interviewed, because we have no control over that population. It is the size that it is. So therefore, this formula, the population variance of a population, is the identical formula of the sample, except the -1. So therefore, the standard deviation of the population is totally the same thing. So what are we going to do to get there? Take the square root, and lo and behold, look at that. If I just cover that up, there's our standard deviation of the population. Amazing, amazing, amazing. Okay. I hope you're enjoying my excitement about that. All right, so now, in the next, that's it. So in the next video, we'll move on to Chevy Chevs and empirical, and we're going to have some more fun.